So let's write the Turán theorem, 1941. It says that for all integers Rn, where r is greater than 1, every graph G which doesn't have a complete complete R-partite graph as a subgraph of a... So you can't find it. In other words, you can say we can't find a copy of Kr in G. With n vertices and extremal number of n Kr edges is a Tr minus 1 on n, is Turán. So the proof, the proof is very simple because we just apply induction on n. So first I should give you an example because otherwise you may think that it is complicated. So again, this is an example of 3 of 8. We have 3 partite. This is 3 partite. So by 3 partite, I mean at most you have at most 3 vertices in each independent set, and then we connect them together. By induction, we fix this and we add some vertices, just one vertex to each independent set. So because it has a complete copy of K3, it has a copy of K3, I mean this is connected to all of them. This is connected to all of them. This one is connected to all of them. This one is connected to all of them. Same as this one. And also this one is connected to all of them. This one is connected to all of them. And this one is connected to all of them. So we fix for n that we apply induction on n. So the number of edges of graph G, your original graph, is less than equal to your Turán number n minus r plus 1, because we have assumed, by induction, we have assumed that we know the number of edges. And then we try to count. We are just counting. You know, in combinatorics, we just count. And we want to count what if we add another vertex. So you see, we should add, we should count all of these edges. And r minus 1 choose 2, because, for example, r is here 3. So it is because it is 3-partite, and we have r equal to 4, so it is 3-partite, and 3 choose 2 is the number of the new edges that new vertex has induced. I mean, has forced us to make connections. And so we have also another term which is n minus r plus 1 times r minus 2, because each vertex has just each new vertex that we add has the neighbors for each new, has r minus 2 neighbors for each new vertex. For example, this vertex has r minus 2 because r is 4, so it is 2 neighbors. It has 2 neighbors, and And also we should add r minus 1 choose 2 that I explained why. And if you add all of them, it becomes the Turán of r minus 1 of n. And since G is extremal for Kr, so this is equality. And since Kr is not inside G, each of the sets V1, V2, these are independent sets. So they become independent, and you can have a partition like V1 union of V1 and V2 and others. So we conclude that G is R minus 1 partite. I mean, you cannot find any other configuration that has more edges than this. So it's a kind of balancing is intrinsic in the work of Turan's. And for example, here you see how you have to make it balance, a kind of balancing. You cannot have in each independent set, you cannot have just one vertex, because it can't become balanced. And so this is another way to look at that, and it is related to chromatic number as well in my future lectures, and you will see that. And when I say T, you can write Turán graph as T and R as well. I mean, some books like to write it like that. And R is your chromatic number, and N is in number of vertices as usual. So the number of edges is R. We have R partite, choose 2, because it's an edge. And then among, you have n vertices, okay? So how could you divide it into different parts? So we have R partite, so we have R parts, so n divided by R is if you square it, then it becomes number of edges. And if this is for if R evenly divides n. So if R evenly divides n, then this becomes R minus 1 times n2 over 2. But if n isn't evenly divisible by R, then assume that S is the remainder of that. And then the Turán graph becomes, so the number of edges is Tn. So then you have your Turán number, you have some extra vertices because it's just the remainder of that. Extra vertices. So the number of edges, T small stands for the number of edges of Turán. And this becomes the number of edges when you have, we don't have a remainder. And what happens is that plus S choose 2. And if you simplify this, it's very easy to simplify that. When you simplify that, it becomes SR minus S 2R. And then let's go to simplify more. I mean, the Turán graph TR minus 1 of n are dense. And so it's about n2 edges. N2 edges. And you can write the number of edges is less than 1 over 2 n2 r minus 2 r minus 1. So the equality happens only when r minus 1 divides n. So let me give you a remark. So we have only epsilon n2 edges that give us a complete apartheid graph where in each independent set we have s edges for any integer s. For example, k2, 2, let's say k2, 3, we have 3 partite, and in each independent set you have 2 vertices. So all combinations of them. And so let's see the cornerstone of all of extremal graph theory, let's say. Not all of them, some basic infrastructure of graph theory is based on Erdős and Stone, 1946. And it says that for all integers are, I will prove it using regularity lemma, similarity regularity lemma, but I want to state it once because I want to show you how it plays an important role. So for all integers greater than 2 and s greater than 1 and epsilon greater than 0, there exists an integer n naught such that every graph with n greater than equal to n naught vertices and at least tr minus 1 of n plus epsilon n squared edges, it contains your beautiful complete apartheid graph with s vertices in each independent set as a subgraph. So this says that you cannot find a KR complete subgraph in G. But if you add just a little bit, epsilon is very small. If you just add a little bit edges, then you will have your complete apartheid graph as a subgraph. So you may think that this is very obvious, but if you prove it, then you will see that it's so tricky. And although it's very natural and intuitive, but you may see that why it plays an important role in graph theory, and in particular on extremal graph theory. So consider maximum edge density that an n-vertex graph can have without containing a copy of H. So let's define Hn by extremal number of n and subgraph H, divide by n choose 2. The corollary is very interesting because for every graph graph H with at least one edge, you can say that this limit, when n goes to infinity, when you increase the number of vertices, so the order of the graph, you have this relationship. Chi is the chromatic number, so it relates everything to chromatic number. So this is the edge maximum edge density that without having any copy of H. And so this becomes chi of H minus 2 divided by chi of H minus 1. So you see chi, your chromatic number, it appears in all of the graph theory because it has a global nature. And I said the philosophy of extremal graph theory is that to force a subgraph, a local structure, by putting some constraint on the global parameters such as chi. So this is the chromatic number. And the proof is very simple, because it is easy to see that we just need to put R, choose R to be your maximum number of colors, chromatic number, and then it becomes, the limit of TR minus 1 of n choose 2 minus 1 is R minus 2 divided by R minus 1. And since H cannot be colored with R minus 1 colors, and H, of course, is a subgraph of your complete apartheid graph, and therefore your extremal number should be less than your extremal number of n, but your subgraph is now the complete apartheid graph with S vertices in your independent set. And the rest of the proof is very easy, because we fix an S and then use the Erdős-Stone, because this is just the corollary of Erdős-Stone theorem. So we can use Erdős-Stone theorem to say that your extremal number of KRS is less than your Turán number, TR minus 1 n, plus epsilon n2, but n should be large. And then it converges, TR minus 1 of n divided by n choose 2. This converges to R minus 2 divided by R divided by R minus 1. And this is less than TR minus 1 of n divided by n choose 2. Plus the epsilon amount that you add, epsilon n2 n choose 2, and you know that this is just 2 epsilon divided by 1 minus 1 over n. And then the proof is almost complete, because extremal number of n and h divided by n choose 2, it converges to R minus 2, R minus 1. And because you have selected R to be your chromatic number, so this becomes chi h minus 2 chi h. The proof is almost complete. And so let's see that what this corollary says. It means that fewer than n choose 2 edges suffice to force a subgraph H. So extremal number of n and your subgraph is K complete graph RR is between, so there is a constant C1 n2 minus 2 R plus 1 and C2 n2 minus 1 over R. And I should, of course, it's different things, but I should say about Erdős-Zos conjecture. So your graph, your subgraph that you want to forbid it, is that it is, you don't have to have a copy of that, is that extremal of n, and your particular interesting graph that you are asking for is just a tree. So T is just a tree, and they proved that this is less than K minus Rn. And K is you have K edges. So in general, you can do it for any graph. You want to see what is this in general.